rocket equation. I don't know if that's how you pronounce it, but correct me if I'm wrong. So before we have a rocket, it's moving with some mass m, and it has velocity v. Okay. Now the way a rocket works is that it expels mass in order to move faster, right? So let's have a look at what happens after. After some little change in time, we'd expect our velocity to increase, right? That's what a rocket should do, right? And the mass, because we've expelled some mass, it should decrease. And we're just going to call these delta m and delta v, right? Just a small little change, right? So our mass over here, just make it look like a circle. And it's going to be moving with some exhaust velocity. Okay, we're going to call it v exhaust. Okay, but because our arrow is this way, it's pointing that way, it's going to be negative, right? Negative. And one more thing is, because we are moving at v beforehand, okay, we're moving at v, we should expect that this mass over here should also be moving at v. Okay, so v minus the exhaust velocity, right? Think about, being in a helicopter, you're moving at 70 meters per second, and you drop, you drop something, you drop a ball. That ball should still be moving at 70 meters per second horizontally. So we'd expect the same thing here, right? If we're moving at v, that little thing that we just let go of should be also moving at v minus the exhaust velocity that we pushed it at. Lovely, right? We got that out of the way. Let's see how the equation fares. And I think the best thing to do here is use the conservation of momentum. Okay, it's not a collision, but we can still use the conservation of momentum, because the momentum is always conserved, and there are no external forces acting on it. That's what we've assumed, no external forces. So I think conservation of momentum is the way to go. So the momentum before is equal to the momentum afterwards. So the momentum before is quite straightforward. It's just mv, but the momentum afterwards is going to be that little delta m here times by v minus v exhaust plus v plus delta v times by m minus delta m. Cool. Now let's just keep doing this. So we're going to have mv equals v times delta m minus v exhaust times delta m, and we're literally just going to multiply this out. It's just a bit of algebra. Okay, it's a bit boring, but let's just get this done quickly. Cool. All right, now let's see what cancels. So the mv's cancel. Delta m, it's a v delta m and v delta m. These cancel. So if we add this to the other side, we should be left with this. And the next step, I think, you can see coming is we're going to do a bit of calculus, right? So if we're going to do some calculus, we want to change this delta into a d. Okay, so we're going to change that delta into a d. Now we're thinking of a finite change going into a really, really small change. So what we're going to have is going to have vex dm equals m dv minus dm dv. Now, the interesting thing about this dm dv is that dm goes to 0, dv goes to 0, which means that dm dv will definitely go to 0. Okay, it is not going to be a constant value. It's literally just going to go to 0. So we can ignore it. Okay, it's negligible. Doesn't matter. So yeah, we're just going to be left with this. This is divided by m on both sides. So we should be left with v exhaust dm over m equals dv. And now we can integrate, right? We got m on one side. With the integration, by the way, we are assuming that v exhaust is constant. Okay, so that's a big assumption we're making, which allows us to make the integration. So just put a little integral sign like so. Now where we're integrating from, so here we're going to be integrating from some initial mass to some final mass. Here we're going to be integrating from our velocity that we're currently at to some change in velocity. Now keep in mind, this delta v is different to the delta v we had before. This delta v is just referring to some change in velocity, right? If you're going to, I don't know, increase, if your velocity is going to increase by some amount, that's kind of the change we make, right? Because we're going from some initial mass to a final mass. Okay, let's go ahead and integrate. It's a very easy integration, just v exhaust here, and you're going to have ln m, not ln of m, but we are integrating from m0 to final mass, and here literally just going to be v. But we're integrating from v to v plus delta v. Okay, and yeah, just some basic integration here. V exhaust, you're going to have ln of mf minus ln of m0 equals v plus delta v minus v. V is cancel, and we can use our log laws here to get everything nice and tidy. So we're going to be left with this equation here. Okay, there we are. Right, so just to recap, Vex is our exhaust velocity, mf is our final velocity, which, not final velocity, so our final mass that we're going to have. m0 is the mass of the propellant that's currently in there, and delta v is sort of the amount of velocity that has to increase in order to make that change, right? So it's more of a change of velocity. So yeah, I thought it was pretty cool, right? I mean, you know, using the conservation of momentum, you can use it really in any case. The conservation of momentum always holds. It doesn't need to be in a collision, okay? Like most people think. It can be even in this, and you can see how the mass changes. So yeah, I'll see you guys in the next one. Thanks for watching.